So we have proved yet that the function z as defined here, z of x is equal to expectation of integration 0 to infinity f of wt e to the power of minus alpha t minus 0 to t kws ds. So this thing, this zx satisfies the equation half of Laplacian z. So since we have considered only one dimensional case here, so we have done that half of z double prime, the second derivative of z, is equal to alpha plus k times of z minus f. Okay, so only thing is that in this proof something is remaining that we have not proved, that I mean this z is continuous, z double prime is also continuous, and z double prime is only piecewise continuous. We have not proved that. That we need to do here. So we need to show the continuity properties of these z prime and z double prime. So here exactly the earlier expression, only instead of w0 is equal to x, I am writing w0 is equal to 0, and f of wt becomes f of x plus wt. So expectation of integration 0 to infinity f of x plus wt into e to the power of minus alpha t minus integration 0 to t k of x plus ws ds. Okay, this whole thing is integrated with the t variable dt. Okay, so this is the expression of zx, we are recollecting it here, and here this thing f of x plus wt into e to the power minus alpha t minus integration 0 to t k of x plus ws ds, this whole quantity is less than or equal to f of x plus wt into e to the power minus alpha t. Why? Because k is non-negative. Okay, so here this right hand side, this thing is Elon function with respect to this Lebesgue measure with respect to t, because this is integration with respect to Lebesgue measure on two time variable, and probability measure and integration with respect to the probability measure. So here this whole thing is in L1 of the, with respect to this product measure. So what did we obtain? We have obtained that this left hand side, this integrand is dominated by some particular L1 function. Okay, and again we see that okay, the map x to expectation of 0 to infinity f of x plus wt e to the minus alpha t dt, this thing is continuous. How do you do that? This continuity is obtained by taking limit inside these integrations, and that can be done only if that you can get dominated convergence theorem, and that is due to the condition on f which is quoted in the statement of the theorem, that this thing is finite. And so we are here. So here this map x to this thing is continuous, and hence due to the dominant convergence theorem, the continuity of, so here x to f of x plus wt into e to the power minus alpha t minus 0 to t k of x plus ws ds for almost every t and omega, that implies the quantity. I mean, why that continuous time? Because w is a Brownian motion, which is continuous path process, so it is continuous with this t. Here also we have continuity with this t. Here also we have continuity with this t. Okay, so but we are not looking at that. We are looking at for every t and every omega, that continuous map of x to f of x, this thing. So from here what we get is that this map from x to expectation of integration 0 to infinity f of x plus wt into e to the power of minus alpha t minus 0 to t k of x plus ws ds. Okay, integration w0 is equal to 0. So this thing will be continuous. Okay, now what is this? This is exactly zx. So from here what we are going to get is that x to zx, this map is continuous. Okay, then what we do is that we consider that dkz, this is set of all discontinuities of the function kxzx. Okay, so here since we have obtained that z function is continuous, so it has no point of discontinuities. So it means that if k into z has any point of discontinuity, that is coming due to the discontinuity of k. So the set of all point of discontinuities of the function kz is subset of set of all discontinuities of the function k. We cannot just say that this things are equal, because sometimes point of discontinuity is of k, I mean, because may not be point of discontinuity of kz, because say for example there say z is 0 or something, okay, so you may not get that discontinuity there, but we can say that this is a subset of this dk. So here we write in words that kz is discontinuous at x, that implies that k is discontinuous at that point x. We now show that wish to show that the z prime, that is the almost everywhere derivative, okay. So here, because we cannot talk about derivative everywhere, correct, because it is z itself need not be differentiable. I have not proved here, just I have proved that z is continuous. So this z prime, okay, so we are now showing that okay, it is also continuous. So z prime is also continuous. How are we doing that? So first we look at 8. So 8, here we see that half of z double prime is written in this way, okay. So this can be integrated out, so we want to do that here. So half z double prime is equal to k of x plus alpha times z minus f, okay, for all x. This is true when our set minus is missing, set minus df union dk. So for those cases this is true, and then we integrate out. So we integrate from 0 to y, half z double prime, and here on the right hand side what we see is that this 0 to infinity k x plus alpha times zx dx, okay. So what do we know? Only that z is continuous, and of course for k we know that is non-negative, etc., and piecewise continuous, of course, and f is the function, given function what is mentioned earlier. So here when we see that f is piecewise continuous and that 0 to y we are integrating, here we are using the L1 look property of function f. So what we do is that at left hand side the integration of z double prime is z prime, okay, this is second derivative, so we integrate, so we get to the first derivative here. So z prime y minus z prime of 0, so that minus z prime of 0 I take on the right hand side. So z prime of y is equal to z prime of 0 plus 2, this half comes here on the right hand side, so 2 times integration 0 to y, okay, k of x plus alpha zx dx minus 2 times 0 to y f of x dx. Now here if we want to confirm the continuity of z prime from here, we really need the integrand is locally integrable, okay. If integrand is locally integrable in L1 loc, we could say in short, then this integration as a function of y is indeed continuous. However, that is not yet clear, so we need to check for continuity of this term with respect to y. We need to check that indeed that this product is in L1 loc, okay. So for alpha z we don't need to bother, because z is a continuous function. Any continuous function is in L1 loc, correct, because you take any compact set, okay, and on a compact set continuous function anyway bounded, and there it is therefore integrable. So only thing is that this this product etc is in L1 loc, that requires proof. And for f, what happens that the condition what we have on f, that I mean that integration that is finite, okay. So from that we understand that whenever we consider I mean that f is in L1 loc, if f is not in L1 loc, that we would not have got that condition, because we had multiplied something, but that is it is minus alpha t, okay. So that thing is also a non-zero quantity. So we get continuity of this term with respect to y, but for this we need to do something more. But if you do this, then we would be able to ensure that the first derivative of z is also continuous with respect to the y variable. Now to prove that k times z is in L1 loc, okay, it is sufficient to prove that the d alpha of mod kz is finite. Why is it so? Because g alpha mod kz, as we have done, the g alpha of f is finite, that implies that f is in L1 loc, that in that integration. So let us recall quickly what is g alpha definition. So this is g alpha definition. G alpha of g is equal to this function, right? Correct. So here g is there, and e to the minus alpha t is there. Or if you want to remove this expectation, etc., then this is without expectation, correct? G of y into e to the power of some number, some function which is strictly positive function, okay, and then dy. So if this is finite for all x, that ensures that, okay, this function g is in L1 look. Okay, so we do this here. We want to prove that kz is in L1 look. We want to prove that j alpha of mod kz is finite for each and every x here. Okay, so for doing this, I mean, we have not treated mod of kz before, because we have treated g alpha of kz. Okay, so here for the first time we are doing it. So we are taking z hat of x. So this z hat of x is defined as expectation of mod of f w t e to the minus alpha t k w is ds. Okay, so now here it is clear that I have mod here. So this is not less than or equals to zx, okay, because zx has just f of wt without any modulus. So we know that zx is less than or equals to mod zx, and therefore now we can take modulus both sides, but right hand side is always non-negative, so mod z is still less than or equals to mod zx. Okay, you understand? The zx, we first that prove that less than this, and then this is non-negative, so mod of zx is less than or equals to z hat of x. Okay, hence, so here actually mod of zx is like mod is outside. Okay, so when you take mod inside, you get less than or equals to sign, correct? So mod of z is less than or equals to z of z hat of x. So hence g alpha of mod kz, what is this? This is where you are going to have mod here. Okay, so that is less than or equals to g alpha of kz hat. Okay, because k is anyway non-negative. Okay, so when we want to write down this mod kz in this whole expression of the integration, so here let us go back to the definition of this. So this expression we look at. So here if you have mod, so then k is anyway non-negative, and if you have kz, so mod z would appear here. Okay, so there you have z hat here. Okay, so mod z is less than or equals to z hat, so that we can write down here z hat. Okay, z hat k alpha of k z hat x. So monotonicity we are using of g alpha. Okay, now this g alpha of kz hat is exactly equal to g alpha of mod f minus z hat. How did you do that? We do that because of earlier equation what we have established here. G alpha of f minus z is equal to g alpha of kz. Does not matter what f I choose. If I would have chosen f here mod f itself, then I would have got g alpha of mod f minus this thing. So instead of z, I would have got z hat there is equal to g alpha of k z hat here. So that is the thing we are using here, that this g alpha of k z hat is equal to g alpha of mod f minus z hat x. Okay, I am using that earlier result which we have already proved. Okay, so now this quantity, is it finite? Yes, it is finite, because z hat, I mean, coming from here, the condition on f is such that this is finite. Okay, so z hat is finite, because here we have even some quantity which is even less than 1. So our condition was that mod of f of wt e to the minus alpha t, only that part. Okay, that is finite. Here we have even some negative term here, so it is smaller than 1, so that is finite. And here this part is also finite because of that assumption of f. So all these are finite. So what we have obtained is that g alpha of mod kz of x is finite for each and every x, and that is the thing we were looking for. Then we can say that, okay, kz is in L1 look. Since kz is in L1 look, so this thing is continuous with respect to y variable, or in other words, z prime is continuous with respect to y variable. Okay, so till now I talked only about z prime. now we should look at the z double prime. So here z double prime is coming from the equation itself, okay, because half z double prime is equal to this thing was there, but now you are multiplying 2, okay. So did you multiply 2 properly? Half z double prime is equal to k plus alpha z minus f. So I should got 2 times f here, 2 times. So here a 2 missing. So z double prime of x is equal to 2 times of alpha plus k x z x minus 2 times of f of x, okay. So this is true for all x, which are in R but not in df union dk. What happens that because we did not get this equation for all R, but we have obtained only for these points, which is not in the point of discontinuities of f and k. Actually kz we had, but we are dropping kz by k here, okay. It is just because that this is a larger set. So since we are subtracting by a larger set, so still this equation holds, correct. So still this equation holds. So this equation we know for this type of point x. Now this right hand side we look at this. So this is this piecewise continuous, f is piecewise continuous, and k is also piecewise continuous. Z is continuous of course, but then this multiplication we can only talk about piecewise continuous. So this right hand side is continuous on this R subtract the point of discontinuities of f and k, okay. So on this region, okay, on this set, and since this is continuous on this, so left hand side is also continuous on this set, okay. So we can say that z double prime is continuous on R except on df union dk, okay. This is trivially true. So or in other words that z double prime is piecewise continuous, okay. So this proves this theorem. So what is the theorem? That what we started in the last lecture. This is Kack's theorem, which says that if f satisfies this condition, okay, this integrability condition, and k is of course non-negative and piecewise continuous, then for alpha positive, okay, I mean this is alpha positive, so then z as defined in earlier, I mean integration of f. So this is this one that z is equal to f of wt, this thing, okay, integration of f with respect to this t and expectation this wt. So that expression of z is piecewise C2, that we have proved that z double prime is piecewise continuous, and that satisfies this equation that half z double prime is equal to alpha plus kz minus f, okay. So that is proved. Okay, thank you very much.